Assalamu alaikum, dear students. Okay, in this lecture we'll continue with our discussion on half-wave rectifiers. So we'll be discussing DC diode voltage, which is the eighth parameter. DC diode voltage. DC diode voltage is basically the measure of average value of instantaneous diode voltage. Okay, so this is basically diode voltage, V diode, and it is instantaneous value of diode voltage. Instantaneous value of diode voltage. Now see, when in a half-wave rectifier, when you have so this is, for example, the AC waveform. This is the positive half of input and this is negative half of input. This is V input. Okay, and this is the circuit for half-wave rectifier. This is the load resistor and this is diode D. This is diode D. So the conduction angle is 0, then you have pi, then you have 2 pi. Okay, so alpha is the conduction angle, alpha. So we have two different cases that we have to observe in order to find out average value of instantaneous diode voltage. Okay, so one case is when your input waveform, when your V input is between 0 to pi, 0 to pi, that is positive half. So this is case 1, that is positive half of input. In positive half of the input, our diode D, it is forward biased. When our diode D is forward biased, then diode will be equivalent circuit of the diode is short circuit or forward resistance, or it will act as a resistor with a very small value of resistance. So it will be nearly short circuit. So what will be then V diode in voltage across the diode in forward bias? It will be equal to I into R of F, if R of F is the forward resistance of the diode. And since it is short circuit, it will be nearly equal to 0. So there will be no voltage in positive half of the cycle in first case, when your input will vary from 0 to pi. In case second, when V input varies from pi to 2 pi, V input varies from pi to 2 pi. That is, our V input is having a negative half applied on the circuit, negative half of input. At that time, our diode is reverse biased. And our diode, the equivalent circuit of the diode is open circuit. Okay, equivalent circuit of the diode is open circuit. So therefore, what is the voltage across the diode? V diode is equal to V input, because see, whenever we have an open circuit here instead of diode, the circuit will now look like this. So you have V input here, okay, which is an AC input, and you have load resistor here, and you have open circuit here. So what is the voltage between these 2 points? It will be equal to V input. Okay. So V diode is equal to V input, which is basically equal to Vm sine of alpha. If we assume that input voltage V input is a sinusoidal wave, and it is defined by V input is Vm sine of alpha. This is my input. It is a sinusoidal one. So it will be exactly equal to input. Okay, it will be exactly equal to input, my input. Thus we can say, we can say that V diode, it is nearly equal to 0 when alpha is greater than 0 and it is less than pi. And V diode voltage is equal to Vm sine of alpha when our alpha is greater than pi and less than 2 pi. Okay, so this is the condition. So this is the output voltage that we will have in positive half cycle and in negative half cycle. So therefore we can calculate the average value of this diode. Average value of diode is V diode, which is the DC. It is equal to average value of V diode. And how is average value calculated? It is calculated by 1 by 2 integration 0 to 2 pi V diode into d alpha. Okay. And this is equal to 1 by 2 pi integration of 0 to pi 0 into d alpha plus, that is for case 1, and for case 2, when the conduction or when the input will be from pi to 2 pi, then the integration will be input. What is V diode? V diode, we have Vm sine of alpha d alpha. Okay, so we have two inputs. We are integrating V diode in separate intervals. One, when you have interval V alpha equal to 0 to pi, so that is this one. Another interval when you have interval equal to pi to 2 pi, then this will be the term. And at that time, your input is equal to Vm sine alpha. And during first case, our input is 0. This is how we have substituted these terms. Okay. If we solve it further, we'll be able to find that we will have, this will be now simplified to Vm by 2 pi into minus cos of alpha. Then we have limits pi to 2 pi. First one will vanish because you have 0. First one will vanish, first term. So we are remained with only second term. And if we solve the second term, then we will be able to find that we have to now give the limits only. So integration of sine is minus cos, then limits are there. While we use or substitute the limits, on using the limits, we'll be able to find that the term reduces to Vm by 2 pi into minus 2. So we can say then V diode DC, that is the average value of diode, it is equal to minus Vm by pi. Okay, so this is the average DC diode voltage. This is the DC diode voltage. Okay, V minus Vm by pi, minus Vm by pi. Now the next parameter is no load DC output voltage. So we have ninth one, no load DC output voltage, VDC no load, okay. So this is basically the parameter which will measure the DC output of the half-wave rectifier, DC output voltage of the half-wave rectifier when load current is 0. When load current is 0, that is the open circuit voltage at the output. So VDC no load is basically the parameter which measures the DC voltage of the half-wave rectifier provided there is no load current, that is IDC is equal to 0. Okay, IDC is equal to 0. Or I can also say provided RL is equal to infinity. RL is infinity. Now see, this is the secondary of the power supply where we have rectifier also. This is the secondary of secondary winding of the step down transformer in rectifier. Then we have a diode here and we have load resistor here. Okay, so this is load resistor. So the current that flows through the diode, this is known as IDC. Now see, IDC will be zero. IDC will be zero when there will be no load present. When the load resistance, when this will be open circuit. Okay, when you will have open circuit between at load resistor. What is open circuit? Open circuit is a very high resistance, or we can say no DC current or no load current will flow when load is very high, when the resistance of when load resistor tends to infinity. When load resistance tends to infinity, then no DC current will flow across through the circuit, and whatever voltage will be calculated across these 2 points, then at that time it will be called as VDC but no load. VDC but no load. It is DC voltage, output DC voltage of the rectifier, but no load. And this will be the polarity. Top will be positive and you have positive, negative at the bottom. Negative at the bottom. Okay. So we have negative at the bottom. And so this is V diode. Okay. Here, what is the voltage across the diode? We have already calculated in parameter 8. This voltage is plus minus. This is basically V diode, but it is DC. Okay, V diode DC. Now see, in this circuit, if we apply KVL, you will be able to find that uh, what is the DC voltage in the coil in the secondary of the transformer? It is 0. In the secondary of the transformer, there is all AC present. There is no DC current. Transformer operate on AC voltages. They step down or step up AC waveforms. So there is no DC current present or DC voltage present in the transformer secondary. Only you have AC waveforms. So if you assume that some DC voltage will be there or there is some DC voltage, so that will be equal to 0. So that's why I have marked it here 0. Now in this network, if we apply KVL, we can write down we have minus 0, then we have plus V diode DC, then we have VDC but no load, and this all is equal to 0. This all is equal to 0. We can use this equation and we can conclude that VDC no load, it is equal to minus times V diode DC, minus times V diode DC. Okay, or we know what is V diode DC from equation A above. From equation A above, we know that VDC, then VDC no load will be equal to minus times. What is V diode DC? It is equal to minus times Vm by pi. Vm by pi. So we can say that VDC no load, it is equal to Vm by pi, which is basically the maximum DC output voltage of the rectifier, of half-wave rectifier. Okay, maximum DC output voltage of half-wave rectifier. So we'll move now to the next parameter, full load DC output voltage. 10th parameter is full load DC output voltage, VDC full load. Now this parameter is a measure of, it is a measure of DC output voltage, DC output voltage when a non-zero load current, non-zero load current is passing through the circuit, passing, and a non-zero load current is passing. So VDC full load is the voltage, it is the DC voltage of the half wave rectifier, provided that our load current or DC current is not equal to zero. It is not equal to zero. Okay. So when it is not equal to zero, it means that there will be some non-zero volt current flowing through the load resistor. If we have load resistor here, so some current will flow here that will be equal to IDC. Okay. So whatever potential drop will be at the output, that is VDC full load. VDC full load. So we have VDC full load. VDC full load. This is plus, this is minus. When non-zero load current flows through load resistor, then it is known as VDC full load. What is VDC full load equal to? VDC full load will be then equal to IDC into RL. That is the current through the resistance. Load resistance into the current through this resistance. Okay. So we can say then, therefore, VDC full load is equal to IDC into R of L. R of L. Say, for example, this is equation 1. Okay. This is equation 1. But when load current flows through load resistor, DC voltage drop occurs in secondary winding. And diode due to their non-zero internal resistances, so when load current flows, DC voltage drop across the diode can occur. So there can be a voltage drop across the diode also. So suppose I have a half wave rectifier, we have secondary of the transformer, then we have diode here, and we have load resistor. So this is my load resistor, and this is diode D, and this is secondary of transformer. Whenever non-zero DC current will flow in the circuit, then because of the non-zero internal resistance of the diode, some voltage drop will also occur across the diode, some voltage drop. Okay, so let us call that internal DC voltage drop. Okay, internal DC voltage drop. So between this, it can be internal DC voltage drop. Internal DC voltage drop. Therefore, by taking this voltage drop into account, we can say then VDC full load can be obtained by subtracting these voltage drops from VDC no load. Okay, so in this diagram, this voltage also in the diagram just above, we have VDC full load here. Okay, we have VDC full load here. But if you will see the previous diagram, the circuit is open here. This VDC no load will appear here also. So this is VDC no load. VDC no load because the circuit here, current does not flow. IDC is 0. Current does not flow. You have open circuit. RL is not present there. The load resistance is infinite. That is, it is just like open circuit. So whatever is present in the secondary, that will appear between points of load resistor. So VDC will be the secondary voltage. So I'll assume the same here. So it will be VDC no load voltage between here and here. If we apply now, and you have here VDC full load voltage here. If we apply KVL, Applying KVL, we can see that VDC full load, it is equal to VDC no load minus internal DC voltage drop. Internal DC voltage drop. Okay. So VDC full load, it is equal to VDC no load minus what is internal voltage drop? It is IDC into resistance of the diodes. Say for example, resistance of forward resistance of the diode is R. Okay, so this is forward resistance of diode. So it is R. So we can say then VDC full load, it is equal to what is VDC no load? VDC no load from equation C here, it is equal to Vm by pi. It is equal to Vm by pi. Okay, Vm by pi minus IDC into R. IDC into R. IDC into R. So this is VDC full load. So suppose this is now equation 2. Equation 2. Now see in equation 2, if we see that DC output voltage decreases with increase in load current. Okay. If we observe equation 2, observing equation 2, we can conclude that DC output voltage decreases with increase in load current. With increase in load current. Now see from equation 2, from the circuit, first of all, if the load resistance increases here from the circuit, if load resistance increases, what will happen to the DC current? DC current flowing through the load resistance decreases, because when resistance will increase, the current through the resistor will decrease. Okay, current through the resistor will decrease. So I can say that from circuit, if RL decreases, what will happen to the current, DC current? It will have opposite effect. It increases. And if IDC will increase, now, what will happen to potential drop, internal potential drop? Internal potential drop will also increase. Okay, internal potential drop will also increase. So internal voltage drop increases. Internal voltage drop increases. And if internal voltage drop increases, what will happen from equation 2? From equation 2, if internal voltage drop increases, or from equation A here, if internal voltage drop increases, what will happen to VDC full load? VDC full load will decrease. Then it will decrease because it is a minus term in equation 2. Okay, so we can conclude that DC output voltage, VDC full load, is nothing but DC output voltage when some load is connected there, when certain non-zero load current flows through it. DC output voltage decreases with increase in load current. With increase in load current. What is the load current? Load current is your IDC. So when load current increases, our voltage, output voltage, DC output voltage decreases. Okay, so that is the conclusion in this parameter. Next parameter, we have regulation factor. Regulation factor. Regulation factor is the 11th parameter. Regulation factor is basically measure of change in DC output voltage due to change in load current. So we know that when load current changes, DC output voltage also changes. From our previous parameter, that is full load DC output voltage, from parameter number 10, we concluded that whenever DC current changes, our output voltage also changes. Now, how much it changes, how much output changes with the change in DC current, it is measured by a parameter known as regulation factor. Regulation factor, okay? So mathematically, we can say that percent regulation, percent regulation, it is equal to VDC no load minus VDC full load divided by VDC full load into 100. So this will give us regulation factor, but in percents. So percentage regulation factor is equal to VDC no load divided by VDC full load, VDC no load minus VDC full load divided by VDC full load. Okay. So what is VDC no load? VDC no load we have already calculated in our previous calculations. It is Vm by pi minus, what is VDC full load from equation 2? It is Vm by pi minus IDCR from equation 2 above, just above, okay, divided by, then you have VDC full load is also equal to IDC into R of L. VDC full load, it is also equal to IDC R of L. Now see, we have two equations for VDC full load. One is equation 1 and another is equation 2. VDC full load. Both of them will give us VDC full load. So we are using both equations here. So I'll write down here using equation 1 and 2 here. Using equation 1 and 2. Using equation 1 and 2. Now if we expand or simplify this term, you will see that this term will be gone with this term, and finally we will be left with percent regulation. It is equal to R divided by R of L into 100%. This is the percent regulation. Okay. Ideally, regulation factor should be 0. It means that there should be no change in the voltage with the change in load current. Please remember that ideally, regulation factor should be 0. That is, DC output voltage should not change with change in load current. Should not change in load current. Okay. So ideally, regulation factor should be 0. Ideally, regulation factor should be 0. Then the next parameter is parameter number 12. Parameter number 12. Parameter number 12 is peak inverse voltage. Peak inverse voltage across the diode basically. It is also known as PIV, peak inverse voltage. Peak inverse voltage, it is the maximum voltage which appears across a diode when it is reverse biased. When it is reverse biased. Or when it is in non-conduction state. Non-conduction state in a rectifier. So peak inverse voltage is the maximum voltage that can be applied on a diode when it is not conducting or when it is reverse biased, because in reverse bias diode does not conduct but in a rectifier. Okay. Now peak inverse voltage is equal to V diode maximum diode voltage. Okay, peak inverse voltage is the maximum diode voltage when diode is reverse biased. When diode is reverse biased. What is diode voltage when diode is reverse biased? In reverse bias, diode is an open circuit. In reverse bias, suppose this is a sinusoidal wave, okay, and this is diode, and this is load resistance. This makes a half-wave rectifier, and this is V input, and V input is equal to Vm sine of alpha. Vm sine of alpha. When diode is reverse biased, then diode will be open circuit. Diode will be open circuit. So whatever V input is present here, all the V input will be applied between these 2 points. Okay. So peak inverse voltage is V diode maximum when diode is reverse biased, which is equal to Vm sine of alpha. But the maximum value of this, maximum value, because when diode will be reverse biased, at that time, our input will be negative half. It will be negative half. So negative half, during negative half, the voltage can be smaller, much smaller, and it can be much negative. This is the maximum negative value. So this is maximum negative value. So peak inverse voltage is the maximum negative value that a diode that is applied on the diode, or that a diode can bear. Okay. So for safe operations, we say that for safe operation of a diode, peak inverse voltage should be always less than V breakdown. So if it is greater than breakdown, then the diode breakdown will happen and diode will be damaged. It will not work. So for safe operation, we have to first calculate what is the breakdown voltage of the diode, because breakdown happens in the negative region. You have a diode when it is forward biased, the characteristics are like this. But once it is reverse bias, breakdown happens somewhere here. Okay, breakdown happens somewhere here in negative voltage. This is voltage axis, this is current axis. So when voltage is negative, so how much negative can be applied on the diode so as to prevent the breakdown? That is the maximum breakdown voltage. Okay, maximum breakdown voltage point. So peak inverse should not exceed that. It should be always less than V breakdown. It should be always less than V breakdown. It should be less than that for safe operations. Okay. So I'll stop here. I'll continue with more parameters in my next lecture.